have Cecilia from Gwyneth coming up next to talk about L1 to L2 interoperability and how they're making it fast at Gwyneth. And I'll give her 1 second to get set up over there, and then we'll get started. So thank you very much.
Hi, everyone. My name is Cecilia, and I'm an engineer at Taiko. And we're working on Gwyneth, which is an interoperable solution for L1 and L2 and an inner L2 synchronous composability. And the topic of my presentation today is L1 and L2 interop and programmable block. And this is regarding our design of what we call ultra transaction, which is how we propose block on Ethereum. Right, so just a little bit of context, like last time that I was on Composability Day, I gave this talk about composability, like how we lock the state on L1 and L2 to make sure that the blocks are built. So the context is that a block needs to be built with shared sequencer that facilitate cross-chain call. And L2 and L2 to L2 interoperability can be easily established if two chains are being sequenced in one shared sequencer, and the states are being locked with some shared sequencing protocol. So if we have two chains over here, as long as we obtain the state lock of both of the chain through some protocol, and we build them in a super builder underneath, then as we build this block, these two chains can easily interop with each other, right? So like, and we usually settle those blocks nowadays with pre-confirmation protocol. With inclusion pre-confirmation, you're able to have a promise from the L1 validator that your transaction will be included as somewhere within the L1 block. But however, that means L1 state is not locked. The builder cannot assume anything about previous L1 state, which means we can interop between two chains that we're sequencing for, but we cannot interop with L1. With execution pre-confirmation, we can actually interact with L1 because the validator can promise you the execution outcome of the L1 state. And the easiest form of doing that is actually if a builder wins the PBS auction, which means it monopolizes the building of the entire L1 block. That means as you build the L1 block, which you also build the L2 block at the same time, that's like the basic base rolled up construct, right? If you build the block like this, you can interop with L1 and L2 easily. However, that's also very hard to establish because you cannot count on your builder to win the PBS auction all the time. And also like execution pre-confirmation is very hard to implement and is still being under discussion within the Ethereum sequencing community. So what we have at the best is what's called top of the block pre-confirmation, which means we can read the L1 state from the previous block because that was done, right? We can read the state, L1 state from the previous block and build it as it is. And then we have one chance as we propose to write it back to L1 state at once. So we get like partially synchronous composability with like read and write, and read and write only once, right? So the problem statement that I want to solve today is how do we interop between L1 and L2 freely, like back and forth, with only top of the block pre-confirmation. So, the solution that we come up with at Gwyneth is what we called ultra transaction. So we indeed just propose it one time at the top of the block, but in this top of the block ultra transaction, we do share settlement, and that will update each rolled up state, but also execute all cross-chain calls in one pass. And the intuition behind is that as this one single transaction being executed, the EVM is only instantiated once, which means there's no like unknown L1 transaction that jumps the queue to mess up your state. And upon we obtain the state law at the top of the block, we basically seize control of all of the states across layer 1 and layer 2, right? in the entire lifespan of this transaction execution. And a bonus that we have is we can use what's called transient storage, which is a new feature implemented by the EVM that like initialize these storage slots once during the execution of transaction, but then they're gonna wiped out. They're being wiped out at the end of the transaction execution, which means we can use these transient storage to facilitate message passing as we execute cross-chain call. And another benefit is we get atomicity, because a lot of shared sequencing protocol has difficulties in ensuring all of the rolled up are settles, right? If you facilitate cross-chain call between rolled up A and B, if A settles but B reverts, then you kind of need some extra construct to make sure that like everything gets rolled back atomically. And if we indeed settle everything at once, you kind of have this atomicity at once, because if anything reverts, the whole transaction reverts on L1. That like there's no like singled out settlements that are just leave everything hanging there. Yeah, and we also kind of bring all of the settlement dependency and cross-chain constraints into the EVM. And there's no need for, like I said, external protocol as a coordinator or observer to facilitate the settlement coordination. And that also brings programmability of block space into the EVM, because as you write the construct that constrain each settlement dependency in Solidity, you kind of bring everything in the EVM. So that's what we call programmable block, right? And the facility is enforced by proving the building process of the settlement, the ultra transaction. So the question is like, how do we build this fat transaction then? Like, how do we settle everything together? If you guys are familiar with account abstraction, this should immediately rings the bell, because in account abstraction, a bundler will bundle user operation and settle them on L1 all at once. And that immediately just sounded like a rolled up proposal, which you batch basically L2 transaction and settle them together at once, right? And in this case, for example, we have like Alice has a smart wallet code in her address, and the front end will build user ops as she interacts with her wallet and batch her operation and call this execute function. And EIP 7702 will allows the bundler to submit transaction with like the origin as the bundler, but as the transaction goes out, the message.sender will equal to Alice, right? And how we use this for rolled up proposal, especially in terms of synchronous composability, is that we use our, am I blocking this? We mandate our cross-chain application to inherit this interface, right? So that like if we have a synchronous application, like Uniswap, that has two instances on L2 and L1, which has this account abstraction code that are inherited from EIP 7702, then the proposer can call state update function or relay cross-chain call on behalf of Uniswap. So as you submit the proposal of Uniswap settlement, the transaction.origin will equals the proposer, and the message.sender will equals to Uniswap itself, right? So you kind of get this like cross-chain call for free if you mandate that like Uniswap L2 has the exact same address as Uniswap L1. You're calling yourself from L2 to L1 with the same address. Right, and the L2 to L1 call will be relayed to execute on Uniswap L1 in the L1 runtime. So this is how we collect all of the cross-chain calls. So for all of the calls that are initiated from L2 to L1, we collect them as user operation, and we relay them to the L1 execution environment. And I find it very useful to separate this concept of L2 runtime, L2 build time, and L1 runtime. So in L2 build time, a shared sequencer has access of all DB locked at time t if the shared sequencing protocol implement the state law. And Gwyneth allow this, so basically we implemented this builder from us that we allowed that to like switch the DB instance at a function call level. Yeah, so if a transaction goes from Uniswap L2 that invoke Uniswap L1 at build time, we can basically emulate this transaction with the state that were being read from previous L1 block and propose the state and propose the execution result of L2 at time t+1 as we do the roll up operation. And after this, the L1 part of the call is being emulated again in L1 runtime, we kind of progress the L1 state as well. So that's how you complete a pass of L2 to L1 call. However, on the other hand, if you have a call that is being instantiated from L1 calling to L2, this call is also being rolled up to L1 and being emulated in the L1 runtime. But the nuances is that the L1 runtime doesn't really have access to L2 states, right? If you run a Geth node that are syncing this transaction over there, it actually cannot execute what is happening on L2. So the L1 EVM needs a Oracle access to the L2 output. So we still emulate everything, but then we record the L2 output and put it in the Oracle. The Oracle in itself functions as a lookup table to pre-process information. Yeah. So for different calls, we have we record the input that we emulate on L1 runtime, and we also record the output and put it in a extension Oracle. And we also have another path to implement the synchronous composability that is state diff, right? So instead of relaying the entire call, we kind of just directly build everything at the build time and just update the results, right? If we have currently our implementation for L2 instances are if we have this transaction going from L2A to L2B, the builder will directly collect the state diff caused by A on B and directly apply it to local DB, and also propose the state delta to DA. So this is what our blobs will look like on L1 DA. So for different transactions, for different chains that we're sequencing, we'll have transaction list of different chains and also the state diffs that are caused by different chains to each other, right? And if a state diff touches L1, right? If a Uniswap L2 instance causing state diff on L1, instead of relaying call, another way we can apply the updates is to update the L1 slots directly. So for each contracts that are being updated on L2, we kind of enumerate everything, and for each slot, we'll just enumerate out of the slot and just change the number, right? You directly update the result of the pool on Uniswap at the end of L1, at the end of the rollup proposal. So this is how we do different passes of synchronous operation. And this is the runtime view of a rollup proposal, right? At first, you update the extension oracle, and then you relay the call, and you apply the state diff, and then you settle your L2. And within the L2 settlement, of course, we have DA of different L2 that contains the state deltas caused by L2 calling each other. And the nice thing for this is that we can also just relay regular account abstraction bundles. We can insert account abstraction bundle as we relay the L1 call. So a super builder also have extra space to extract more L1 MEV. So if a L1 transaction is being fetched by a L2 RPC, we can also just sequence that and propose that as a AA bundle, right? And also the extension oracle in itself can be considered as a syscall calling into the EVM runtime to prepare everything for whatever that you want to execute afterwards. There's some realization that we have as we implement this. So Ultra transaction is a rolled up proposal as much as a AA settlement. and Ultra transaction implements execution pre-confirmation of L1 transaction as you sequence all these user operations, because like it's being sequenced with certain with a deterministic order, which in itself upon like the L1 state law, which in itself is execution pre-confirmation. And the cross-chain builder is a shared sequencer as much as a pre-confirmation gateway. And this paradigm works for almost all base rolled up on the sequencing protocol. The validity of the rolled up proposal can be enforced by two ways, right? We can either put the entire builder instance into a TAE, meaning we prove the build time, or we can just prove the runtime, meaning we can prove the individual settlements of each rolled up within rollup's A's view or rollup's B's view. Like we prove these settlements separately, and we aggregate the proof as we prove the L1 settlement within L1 EVM, right? And then we constrain out of the input-output pair and the state diff in the lookup tables. So in that, we kind of automatically get proof aggregation on L1. So that's like amortizing costs, right? And another benefit of this is the fact that these individual base rolled up layer 2 can be non-EVM instances, right? Imagine if this is a Starkware rolled up, like with proof aggregation, we can also tolerate the fact that the proof system underlying is different because proof aggregation is recursive, right? I'm gonna give like 2 examples to battle the point that people are talking about, like saying synchronous composability is overrated, right? So the first example is, how do we migrate Hyperliquid on Ethereum as an app chain? So as you know, that Hyperliquid is a perp DEX which has order books for long and shorts, and a clearinghouse that updates margin and liquidate users, and also a oracle for price, right? We may as well implement the order book as a L2 mempool that sequence the order, and we can implement the clearinghouse as L1 contracts that also settle the roll-up state, right? And the extension oracle in our design can be used as a price oracle, right? I think in Hyperliquid, their consensus protocol mandate every validator publish price feed every 3 seconds because price is very important. And if this type of application is an Ethereum rolled up, then another benefit that it has is it gets interoperability to Ethereum L1 pricing, like Chainlink. It can access Chainlink Oracle or Uniswap price for more, that can be more precise. And also given the design that we have for like L1 and L2 Interop, the deposit and withdrawal can be done in one block, right? Another example that I have is with Uniswap, right? Like we don't think UA chain can actually solve liquidity fragmentation because they're trying to convince everyone to like move their money to UA chain. And I think a better solution is perhaps just leave all of money on L1, right? And with our design, you can have a Uniswap that inherit our interface that has a L2 mirror instance with empty liquidity, right? And what you can do is that the builder can process L2 initiated swap on L1 as a user ops that basically implements application-specific sequencing. So this Uniswap L2 instance will be like by default, will be essentially sequencing L1 Uniswap swaps, the L1 swaps as user operation. So that it's basically sequencing for this application specifically, right? And L2 user can borrow L1 to L2 flash loans, and in that case, like you take money out of L1 and immediately pay it back to L1 and do whatever you want on L2. And in that case, the Uniswap L2 contracts only function as a liquidity entry point to L1. You don't need any money on layer 2. So where does that come together, right? people are kind of bearish in the adoption of shared sequencer because no rollup will easily give up their sequencing right. Well, we kind of agree, but I'm more optimistic in this because I think that the adoption of a shared sequencer kind of comes together with base preconfirmation, right? So as long as the adoption of base preconfirmation is going well, we're good, right? And I also think that base app chain and interoperable apps is the future of Ethereum application. Like now is 2025, like why would you like deploy another contract and let your user tolerate 12-second block time? You may as well adopt the latest, infrastructure to have like pre-confirmation, fast transaction, and also interoperability if you deploy yet another rollup or chains, right? Yeah, and I think at the front end, wallet should just send bundle directly to the validator, and the validator issue pre-confirmations to it, and hopefully with account abstraction, you have more programmability on the gas pricing. With this, potentially, you can have a subscription model for Web3 wallets, right? And the gateway should collaborate with validator that provides proposal commitment as a service. And service like that will include rolled up settlements, like bundle settlements, and rolled up interoperability. And on the back end, I think, in fact, rolled up is a subset of self-sequencing application with its own subdomain, right? If application-specific sequencing sequence for apps that lives on L1 address space, then rolled up is, in fact, a subdomain with its own address space, right? And currently how Taiko, which is the first base rolled up that are live on mainnet, how we work is that like the builder is sitting behind a gateway, and we submit proposal to the validator, which issues a pre-confirmation. And with base pre-confirmation, we have multiple builders sitting behind the gateway that we can easily implement Interop with this, right? So with intra-cluster communication, we basically have one builder sequencing for multiple domains. And solution like Gwyneth will be the interface that offers the programmability for interoperability, right? And if we have intercluster interoperability, then with a rollup that adopts like a different stack, like let's say the other rollup using an OP stack, then we can have a shared sequencing protocol. But in any case, it kind of makes sense for the gateway sitting in between to facilitate message passing. So I like to use Fabric, which is a coalition of Ethereum sequencing community to accelerate the adoption of base pre-confirmation. I kind of want to use Fabric as an end node for my presentation because for all of the infrastructure that I just mentioned on the last slide, is being carefully considered and put together. And I think that like as long as we have more validator onboarding pre-confirmation protocol, the future that I was describing is not far. Like we can easily build Hyperliquid on Ethereum, and we can build something like Moonshot on Ethereum as well. And that's the end of my presentation. Thank you.